right, good morning. So last time we talked about granular filtration. We'll pick up here for today. It should hopefully be kind of a short lecture, and then we can go take a visit during class hours to my lab to see the filtration units. So that's kind of my plan. Hopefully it doesn't start raining and pouring on us. So maybe we'll delay it if so. If I've got my my head straight, then the homework's due next time, and then we have an exam review that day, and then the exam will be, I guess, a week from today. All right. So today, then, we'll wrap up the last bit of content that will be on our first exam. So that'll be, we'll cover basically kind of the review of reactions and reactors and mass balances, sedimentation, coagulation, flocculation, and granular filtration. That'll be the exam number 1 topics. We'll go in more depth on that next time. Okay, for today, really what I want to focus on is partly how to know when we need to backwash, and partly, given that, what quantity of water can a filter produce in terms of a full cycle. So including the water that's going to be used to backwash, and that's water that was produced and now is wasted, and including any wasted water from rinsing and all of that. Okay, so we talked about the design criteria last time, and we said, if we're looking at turbidity, for example, I think we talked about head loss time limits. And for turbidity, if we think about a system that has some rinse period, and I don't think I drew this last time, but if we had a rinse at the start of our cycle, and then at the end somewhere we'll take it off and backwash, and then we kind of end our cycle, the turbidity will probably actually, and let's imagine we have a cutoff limit where if it goes above this level, we have to stop. So then if our turbidity, we're monitoring it as we start the cycle, it's very likely going to spike almost immediately above the limit, or perhaps even start that way, until maybe 20 minutes or so. It should start dropping off, and then usually we switch from minutes to hours when we're talking about like the rinse time versus the cycle time. So, if I was drawing this to scale, we'd have kind of like a sharp decline like that, and then it'll sort of slowly increase, and then we'll hit that backwash point where we have to cut it off. And then, of course, if we're backwashing, we're not monitoring it, but you get the picture. So something like that would happen for our turbidity, because in the rinsing step, we've got lots of particles that were dislodged and now are sort of freely floating around and need to be, we need the sand grains themselves to settle in order to have a chance at capturing things. So that rinsing step or priming step is really important, and you can see very clearly if this is what's happening, that's why we're not going to use water being produced in the first few minutes of operation. Okay, so last time we drew a line something like this, where a cycle time, we have a rinsing or ripening stage, a production stage, air purge, backwash. So I just left all that drawn up here for you. So the question becomes, how do we know how much water we're producing as a net value? And so a typical production rate during that production time, so when I say production rate, we're really talking about that point, would be something like 2 to 20 gallons per minute per square foot, or 5 to 25 cubic meters per square meter per second. This is the same as saying the loading rate. So we'll say the production rate and the loading rate are the same. That is lowercase v underscore a. So that's the term that our book uses. And what this is describing, if you look at the units, this is a kind of like a flow rate, so gallons per minute, but a flow rate divided by an area, right? It's the flow rate passing through an area. So that means if we had some filter bed, of course we've got some length and width, and water's passing through it with some flow rate. Well, this loading rate is describing it in terms of that surface area, and if we cancel out those terms, that becomes a velocity term. So Q over the area is analogous to a velocity, right? So it's essentially a flux. It's the amount, I guess the flow rate through an area or through some plane. That's what we would call a flux. We'll come back to that when we talk about membrane filtration after our exam. But essentially, what this is giving us is how fast water is being pushed through the filter. Okay, and that relates to how much water we're producing, the Q, and we call this our loading rate. So in some sense, it's how quickly can we add water on top of the filter and have it go through, assuming that we're not accumulating more water or whatever. Okay, so that's and that would be Q for one filter, right? If we're talking about that one filter. Of course, we could talk about area of all the filters we have in a treatment plant or something, but typically we'll single out one filter and then extrapolate to a treatment plant. So I have a note down here that a flow rate for the treatment plant, keep that distinguished in your mind from the flow rate of one filter. So if you're dealing with the flow rate in the entire treatment plant, you have to multiply it, of course, by all the flow rate you get through, 10 filters or however many filters you have. Okay, so it's a pretty simple concept. What I want to highlight here again is this loading rate is really talking about what's happening during that production stage. Okay, if we want to know something about the effective rate, we'll need a different equation, and we'll look at that in a moment. A lot of times in the backwash, we'll use either the same loading rate, just in reverse, or sometimes we'll increase it, maybe even double it to go backwards. So a lot of times we'll have a different backwash rate. The rinsing rate is always going to be the same because we just want to start operating the way we're going to be operating. So we'll have the same VA for the rinsing will be equal to the VA during production. And I'll write a note here. So the loading rate for backwash is not necessarily equal to VA. I'll say sometimes. Sometimes it's equal to VA, or sometimes up to 2 VA would be typical. Okay, so in terms of backwashing rates, keep an eye out. If nothing was specified in a problem anywhere, you might assume that it's the same. Okay, but usually I'll try to make sure I specify. Okay, so let's talk for a moment about these filters in terms of efficiency. And when I say efficiency, really what I'm talking about is the efficiency of water that is that they're producing. So how much water do they produce compared to how much do they waste in the backwash and rinse steps? So if you had a filter you could operate for, let's say, 10 years straight and backwash for 20 minutes, that'd be a very, very efficient filter because 10 years of operation, that's going to be a lot of water compared to 20 minutes wasted. So this is going to be a function of the volumes of water produced versus wasted. And our filter efficiency equation we have here, nu is equal to that volume filtered, so F here for filtered, minus the volume used for backwash, minus the volume used for rinsing, divided by the volume that was produced during filtration. So each of these are written out here. Of course, we're going to use cubic meters here. I guess you could use gallons if you wanted to. Typically, we'll just be in meters. It's pretty handy to be able to convert using meters when we've got the length and width of a system pretty frequently in meters. Okay, so what we're looking at on our timeline here is our VF is produced during that production stage. We have, of course, VR during our rinse, VB for our backwash, and we're not using any water during our air purge, if we have one. So one thing you'll notice here is, this air purge step is a time during the filtration cycle that we're not pumping water anywhere. Now, if we were looking at, if for whatever reason we had a very, very long air purge step, then, we had to do some other maintenance. Our efficiency on a water basis wouldn't change, but on a time basis certainly would change, right? So that, not a big thing there, but something that could throw a system off. Okay, so to find the volumes, remember what we're doing is we're sending some water through a plane or through an area here, and so in order to find the volume of water, what we need to do is see the time. So if we take our flow rate times time, so let's say backwash time or something, that's going to give us our volume, right? And so if we have a loading rate, then we need to take that loading rate, multiply it by the area, because that's what our Q is in some sense the depth times the width times the length is our flow or is our volume. So that we get the area of the filter, multiply that by our time, that's going to be our volume. And of course, if we want that to be, the volume filtered, then we use the time filtration and call that the volume of filtration. And we need to make sure that we're using the loading rate during production rather than the loading rate for backwashing. Okay, so in this case, if we have our system in meters, seconds, then what we would take a look at is our volume here, volume filtered, area of the filter times VA times time filtration. So then we just really need to know how much time is spent in each step. We also need to make sure that we have VB if it's different than VA. Okay, so fairly straightforward. Once we solve for each of those, we can just put them in our efficiency equation. And essentially, we're just saying, okay, well, we produced 10,000 cubic meters. We spent 100 cubic meters for backwash and another 20 for rinsing. And then we have 9 whatever divided by 10,000 or whatever number I said. And we get some efficiency. So this typically will be, something like 9.5 or better. So you could multiply that by 100, get percentage. So usually the problems that I've seen, these tend to be at the very minimum 90-something% efficient. Of course, you could look at a weird case that was not efficient, I guess, but typically you're looking at 97, 98, something like that. Okay, that efficiency relates a little bit to our effective loading rate. So it is a separate concept. The fact that we do air purges, like I mentioned earlier, can change. Like if we had no air purge, all we had was our backwash and rinse, then perhaps we could get our effective loading rate based on the filter efficiency and not have to do much more problem solving than that. But the effective loading rate is really talking about for a given cycle, like across a full cycle time, what is our loading rate? So instead of just while we're adding water to the filter, like we measured that's our VA. So say our loaded VA is while producing water. This new term, what we're going to call REF, so R effective. REF is if we average the production we get over this whole cycle time. So VA is here. R effective is looking at it averaged over the whole time. Okay? So again, we would have our production, air purge, backwash, and rinse. Okay, so our effective loading rate is going to be this volume filtered over the area of the filter minus the volume backwashed over the area of the filter minus the volume rinsed over the area of the filter. And that's really just keeping our units to be meters per second there. All of that divided by the total cycle time, which is the time of the filtration plus the time of the backwash plus the time of the rinse plus the time spent doing air purge. Okay, so that should be, a little fairly straightforward, right? The total cycle time, we can call all of this here TC. That's our basis here, and we can simplify this by dividing, just taking that area of the filter out of the top there and just leaving that on the bottom with the TC, and it becomes fairly simple. It's the volume filtered minus volume backwash minus volume rinsed divided by area of the filter times the time of the cycle. And you'll see if we compare this to that filter efficiency, it's actually fairly close, right? This time we're on a volume basis, but if you just took the area of the filter there and multiplied by time instead, you can see pretty quickly that you get to just about the same equation. The difference being the inclusion of the air purge step. Okay, so you cannot directly use one piece to solve for the other, but they're close. Okay, so if you have a problem, and we'll take a look at one in a moment, looking for the effective loading rate, and you've already solved for the filter efficiency, you'll have a lot of what you need, but you can't just say, okay, well, if the filter is 99% efficient and the cycle time is, and the loading rate here is like 10 meters per second, then 99% of 10 meters per second, that would be 9.9 meters per second. It'll actually be close, but it's not going to be the correct answer if there's an air purge step. So what I'll say is the new times VA is not equal to our effective, but it should be close. So it might be a handy way to check on it, unless I'm giving you a strange problem that is specifically kind of pointing out that it's not the same. But typically, it should be close in a normal situation. Okay, does that make sense? Any questions before we try a problem? All right. So this is problem 6.9 from our book, page 360. We have a conventional water treatment plant that's treating 2.40 cubic meters per second of river water. The filters in the plant are 8 by 8 meters surface area, and they operate on the following schedule. The filter is cleaned once in each 24-hour period. The backwash rate is 10 liters per square meter per second for a period of 8 minutes. It takes an additional 8 minutes to drain the filter and break up the media with an air ejection. The total filter cycle time of 24 hours, 15 minutes is used for rinsing the filter after backwashing. During production, water is applied to the filter at a rate of 5.5 liters per cubic meter per second. So part A asks what is the filter efficiency, and part B asks what is the minimum number of filters required by the plant. So we're going to take, part A is that filter efficiency, part B is going to be dealing with relating that effective loading rate and scaling that to an entire treatment plant system. All right, so take a bit of time, see if you can solve that. I'll join you in a few minutes. All right. You guys feel like you've got a solution? Almost part of the way there? Most of the way there, something? Okay. So let's take a look. Got this treatment plant. Got all sorts of parameters. I'm just going to shrink it a little bit here. And the first thing we want to know is that filter efficiency. We have that formula for it, volume filtered minus volume backwash minus volume rinsed, divided by volume filtered. So that's going to be for part A what we need. So clearly we're going to need each of these volumes. That means we're going to need the times and the VAs. So, or the VA and the VB. So VA is given. This was 5.5 liters per square meters per second. I'm going to go ahead and convert that into just meters. So that'll be 0.055 cubic meters per square meter per second. And you'll see a theme here every time I encounter a unit. I'm just going to make sure that I'm going to get it in the same terms as I have elsewhere. So in this case, I'm going to change everything to units, and I've got into meters. And so I've got meters and seconds here. So those are probably just going to be what I'm going to aim at as meters and seconds. We were also given that their backwashing rate was higher. It was 10 liters per square meter per second. So when I convert that, it's going to be 0.01 cubic meters per second. And this is just taking 1,000 liters is 1 cubic meter. So we divide that, each of those by 1,000, we get those. Okay, so that's the first kind of unit conversion there. And by the way, these are lowercase v's here for the loading rates. I know there's a lot of v's here with the volumes. Apologize about that. So the volume terms then. So we need a volume filtered, volume backwashed, and a volume rinsed. And to get these, we're going to need time. So we know the total cycle time. We don't know the filtration time. We have something for the air and the backwash. So we'll start with the cycle time here. That was 24 hours. Again, I kind of want to just get everything into seconds. So if we multiply that 24 by 3,600, we should get 86,400. The time for the air purge was 8 minutes. Should be 240, 480. 480 seconds there. The time for the backwash was the same. And the time of the filtration, oh, excuse me, I need the rinse here too. We'll do this. Time of the rinse was 15 minutes. And if we do that, that is 900 seconds. So that leaves just the time of filtration, which is going to be the 24 hours minus 15 minutes minus 8 minutes minus 8 minutes. Convert that to seconds. And according to my Excel calculations, that's 84,540. 84,540. Seconds. Okay, so straightforward, but again, just being aware that the units are really quite necessary here. And also, recognizing that the total cycle time here was given as 24 hours, and then the fact that you didn't have the filtration time, you could solve for it by saying, well, how much time is spent on these other things if the total cycle is 24 hours? So I know it sounds kind of simple, but just bear in mind that it's, the concept of that cycle and the components of it is important to know, and that kind of unlocks the rest of the problem for you. Okay, so those are the pieces. Then the volumes, again, this is just simply going to be area of the filter times the loading rate times time of the filtration, or the associated pieces for each, right? So that for the volume filtered, I went ahead and put all this in Excel so we can just take a quick look here. So the area of the filter, of course, is 64 square meters. So that was 8 by 8. The VA was given. I went ahead and put that here, 5.5 or 0.0055 meters per second. And that time we just solved for. So when we put those together, here we had a volume, 29,758. Cubic meters. So we certainly filtered a lot. We take that backwashing step. That's going to be using the area of the filter times the backwashing rate times the time we spent doing that. And there we had 307 cubic meters. And for our rinsing step, same process, we get 316 cubic meters. So the question is, which rate did I use to find the rinsing? Yeah, that's going to be the loading rate, because when we're rinsing, we're going to operate with the same conditions we would as we're filtering. Right? It's a good question. So, and of course, this is the one that I didn't write out here. This would be the VA times the TR here. So whenever we're rinsing, we're just basically starting up operation as normal. We're just not using that water yet because it's still dirty. So just keep that in mind. As soon as we're done backwashing, we're just going to start it up and start going. We just can't use the water right away. Okay, so with all that, we can solve for our filter efficiency using that equation. And this comes out to be 0.979. So pretty much 98% efficient. So pretty close. So pretty good. And you can leave this as that fraction. You can put it as a percentage. I don't mind either way. Obviously, the equation is giving it as that fraction, essentially the fraction of water that was actually usable compared to the fraction or the amount that was filtered. So that's all part A. So part B is asking us, okay, well, what is the minimum number of filters required by this plant? So we had, Q total that we have to meet is 2.4 cubic meters per second. How many filters does it take to get there given these conditions? So in this case, we're going to need our effective loading rate. As we looked at a few minutes ago, this is going to be that volume filtered minus volume rinsed minus backwash divided by the area of a filter times the total cycle time. Okay, so we have most of that, or actually all of that, since we solved all those other pieces. So we can take a look, and before we get our answer, one thing we should consider is this should be a loading rate that is a little bit less than our actual loading rate. So this effective loading rate should be a little less than the VA, right? So if VA is 0.055, then we expect the effective one to be less than that because we're wasting some water, right? So it cannot be above that. If we get an answer that's above it or that's way, way, way below it, probably wrong given that our efficiency was pretty high. So we can put in those numbers, and we take a look. Essentially, I just put in those numbers directly. You can see where my cursor is, and we got 0.005269. So we'll say 0.0053. Of course, in the calculations, I would carry the info there. And that would be in the meters per second or cubic meters per square meter per second. Okay, so that's our effective loading rate. Now we need to know how much Q total. So the way I like to approach this, and there's probably a couple ways, but I would like to say, well, what is the Q for one filter? And that's going to be this effective loading rate times the area of the filter. And that's going to be, that effective loading rate is a meters per second. The area is square meters, so that'll get us cubic meters per second. So the Q for one filter, I'll call that QF for now. I calculated that to be 0.3372. Okay, does that make sense? Then the last thing we need to do is say, okay, well, Q total is going to be that 2.40 times the Q for one filter times some number of filters. If you want to write it out explicitly, that's the way I do it. So then you can solve and say, all right, I wrote that wrong. Hang on. We'll say the Q total is going to be equal to that. And we know that's equal to 2.4. So we can say, okay, well, if one filter is producing that much, we need to multiply that by some number of filters to get to the total. And so we take 2.40 cubic meters per second and divide that by that 0.3372 cubic meters per second. That'll give us our number. So then with that, number of filters, if we solve that, is 7.12. However, we're not going to install 0.12 filters, right? That does not make sense. We're not going to cut one of these filters into pieces and say, okay, well, this one only has, 10 square meters of filtration area, so that we precisely get this. No, we're gonna round up here and say that should be 8 filters. Okay, that way we have some buffer capacity, and we actually have a little bit more time to backwash if we had to have it. Or we can expand our capacity to treat water for some additional population if the population in the area is growing. Whatever the case may be, that will give us a little bit of a buffer. We could potentially calculate that buffer. And we're not trying to divide a 8x8 filter and shrink it, make a new engineering design, all of that nonsense. Okay, does that make sense? Feel all right about that? Okay, so what I want to do next is have a short quiz on the cryptosporidium outbreak, and then run over to my lab and take a look at our filter there. Seeing 8 people in here and 2 online, so still waiting for one more person to join. Maybe. Sometimes it, you know, if you close your phone or something, it looks like it logs out for a moment. So if that's you might have to get back in. All right, so I'm just going to go ahead and start it. So in 1993, an infamous cryptosporidiosis outbreak afflicted which city? It was based on the reading that we had assigned that first week of classes. Okay, excellent. All right, what type of organism is Cryptosporidium? Okay, so a lot of you got that right. Some of you thought it was bacteria. We'll talk a little bit more about these and the differences after our exam. We'll get into disinfection. But protozoa are larger organisms, still single-celled, but technically larger than a bacteria. Okay. What is a primary symptom of a cryptosporidiosis infection? Okay, good. So most of you got that right. Do that for a moment. Okay. During the outbreak, which water quality parameter was improperly monitored? Okay, so about half of you got it right. It was turbidity. Essentially, they had these granular filtration units, and they were recycling their backwash to an extent, and they were not properly monitoring the turbidity coming out of them, and they accumulated these cryptosporidium spores, and they weren't detecting that they had too much turbidity coming out. They did have fecal coliform problems, but turbidity was the monitoring error in there. Okay, last question. And you're welcome. Which of the following processes was not operating correctly in the treatment plant? Actually, there's another one. Okay, great. So a lot of you got that correct. The coagulation dosing was also failing. So not only were they not properly monitoring the turbidity, they were also not properly doing the coagulation step. Disinfection is also a good guess, but it turns out that we really didn't know a lot about crypto back then, and the disinfection was being applied to the typical extent. And since then, we've improved our disinfection technologies to handle cryptosporidium better. It turns out that it's fairly UV resistant, fairly chlorine resistant, and UV is a good option. Ozone is another good option. Okay, so with that,